equals 0. So this problem is so much fun, we're going to do it twice. Try to contain your excitement. So any ideas? Yeah, Natalie. Okay, good. So just as a reminder, if we were going to graph velocity, so that would be time on the bottom, and it doesn't say, but let's say it's in seconds, and then velocity over here, and it doesn't say, but let's say it's meters per second. So if you do the area on a velocity curve, maybe you get a rectangular shape. I'm making this up. It doesn't go with this problem. But if you got a rectangular shape and the height was 5, that would be 5 meters per second. And if the width was 3, that would be 3 seconds. And if you go 5 meters per second for 3 seconds, then you end up going 15 meters. So I'm just explaining that if we find the area on the velocity curve, that is going to give us distance. Okay, so now let's do the actual problem. So let's graph this velocity formula over here. So the y-intercept is 5, because it's 5 plus 2t. And then the slope is 2. So if you go up 2, you go over 1, up another 2, over another 1, up another 2, over another 1. So there's the graph of this velocity function, 5 plus 2t. And area on the velocity curve is distance. They want the distance on the time interval 1, 3. So that means we're going to find the area from 1 to 3. And this area isn't going to be too bad. It's just going to be the area of a trapezoid, because that's the shape we got. So that's 1/2 times 2 times the 2 bases added together. This is 7. This is 11. Because 2 times 3 is 6, 5 plus 6 is 11. That's what I'm getting the 11. One half times 2 is just 1, and then 7 plus 11 is 18. So that comes out to 18 meters. Okay, what's another way to do it? Yeah, Braden.
Could you take the antiderivative of velocity to get position?
Exactly. If we take the antiderivative of velocity, we'll get position. And position function should help us figure out how far the thing went. Okay, so the antiderivative of 5 is 5t. Then the 2 is just hanging out on that. Then you add 1 to the exponent, so that'll make the new exponent 2. It used to be 1. And then divide by the exponent. And don't forget plus c. And then the information in the problem says s of 0 equals 0. So that tells me that if I plug a 0 into here, I guess I'll go ahead and cross those out. So if I plug a 0 into my position function, from the information given, I know I'm supposed to get 0 out. So then that tells me that C is 0. So now I've got a good solid position function. S of t equals 5t plus t squared. Okay, so maybe where do I go from there then, Braden?
Would you set it equal to 1 and set it equal to 2?
If you wanted to know when the particle was going to be at position 1, then yes, you'd set it equal to 1. But the 1 and the 3 are times. So all you got to do is plug 1 in to figure out where it is after 1 second, and then plug 3 in to figure out where it is after 3 seconds. Good. So a lot of times on the homework, we were setting the whole position function equal to something, but that's because the height was given. And the question was, what is the time? This time, the times are given. Good. All right, so if we put 3 in here, that comes out to 15 plus 9, so 24. So that means after 3 seconds, this particle is at, it's the number line, right? It's at position 24. And then if you plug 1 into this position function, you get 6. So that means after 1 second, it was at mile marker or meter marker 6. And so it went from 6 to 24. So then you can subtract those and figure out that it went 18 meters. Now, I do want to point out that this method only works if it started at 1 and then went just straight to its new position, right? It's possible that it wandered this way for a while and then ended up at 24. But on this problem, I fixed it so that it's starting at the position 6 and it's going straight to 24. So we don't have to worry about that on this problem. Okay, so 24 is the distance traveled. Okay, so luckily we got the same answer both times, right? These kind of problems used to make me nervous because I'd get different answers and then everybody would know. You know, if I only do a problem once, nobody knows I'm wrong usually. But if I do it twice, it's a little dicey, right? You'll all know if I get different answers. Okay, but this one we're good. Okay, now the whole purpose of this, we'd already done this a little bit, but you probably needed a reminder that area under velocity was position. And you'd done this. This was probably more familiar to you because it was more like the homework. But the point of all of this was to point out that these two methods give the same answer. So one method is s of 3 minus s of 1. That was the second method. And the first method was the area underneath the velocity curve. So this was method 1. This was method 2. We got the same answer on both of them, so I can go ahead and put an equal sign in between them just to emphasize that we got the same answer on both of them. Now we know that the derivative of position, the derivative of s, is velocity. And we also know that the antiderivative of velocity is position. The antiderivative of velocity is position. Okay, now, back in the Fundamental Theorem, it's been a few days, but we had little f represent the function, and then we had capital F represent the antiderivative. So if we have little v represent our velocity, we could have capital V represent the antiderivative of velocity. And what is the antiderivative of velocity? Position. So we could call this s capital V if we wanted to. So that means capital V of 3 minus capital V of 1 is the same as the integral from 1 to 3 of V of t dt. So I know I'm making those capitals really big, but that's just to emphasize that this is not velocity, this is the antiderivative of velocity. It's a different function than that lowercase velocity. Okay, so actually this would work for any number. It wouldn't just work for 1 and 3. So it would work for a to b. And also, here's the real thing that I was going for. This works with any function, not just the velocity function. So I could put a little f here and a capital F there. So this is really what I was driving at. If you're trying to find the area underneath little f, you can do it this way. This statement is the same as this statement. I just said, well, it worked for the velocity function, so it'll work for any function. Okay, so that is the fundamental theorem of calculus. We had part 1 last week, so now we're working on part 2. So example 1 was good review on stuff that we sort of already knew, but the point of it was to show that this was true. Okay? And so the formal statement of the fundamental theorem of calculus says that if little f is continuous on the interval AB, so in order for the fundamental theorem to work, you need to have a continuous function. That's all that's saying. And then also, if you have capital F represent an antiderivative, so that's nothing new. I'm just saying we're going to use the capital letter F to represent the antiderivative of little f. So you have a continuous, maybe I should spell continuous right here. You have a continuous function f, and then we have this capital F, which is the antiderivative of it. Okay, so then what happens is the area underneath f can be calculated by taking the antiderivative and plugging in b and plugging in a and subtracting. Okay, so let's say we're trying to find the area from 0 to 1 under x squared plus x squared of x. Yeah. Well, I used to just have 28 people in the room that weren't paying attention to me. Now I've just added another thing that doesn't pay any attention to where I am. Life is horrible being a teacher. Okay, so let's say that this was a calculator active problem. How would you do this problem? Just do math 9 and type the right buttons and boom, you're done, right? Okay, let's say it was before Christmas and it wasn't a calculator active problem. How did you do this problem? It was pretty darn painful, right?
Yes.
We did rectangles.
There was an I.
There was an I, there was an N, and eventually the rectangles got to be infinitely thin, right? So thin that it was the exact area. So just to jog your memory further, it looked like this. Limit as n goes to infinity, sum I equals 1 to n, and then we had a bunch of rectangles in there, right? And that made a lot of sense because we were adding up the area of a bunch of rectangles and then taking the limit. It made sense, but it was painful. Okay, so now today, the fundamental theorem of calculus part 2, the big deal about that is it's the non-calculator way to figure this out without doing this. So this isn't going to go away completely, but it's almost completely going to go away. You still need to be able to understand this. It'll pop up somewhere on the AP test and somewhere in review until then. But most of the time now, we're going to be able to avoid that. Because the theorem that I just wrote down says, how do you do this area? You just take the antiderivative. So the antiderivative of x squared is x cubed over 3, right? Square root of x poses a little bit of a problem, right? But another way to write the square root of x is x to the 1/2 power. So I just add 1 to that. 1/2 plus 1 is 3/2. Then divide by the exponent. And don't forget plus c. But notice over there the word any antiderivative, right? You see the word any in front of antiderivative? So that means if I want, I can make my c 5. Because it says any antiderivative will work. If the question says find every antiderivative, then you put plus c to mean, hey, I could plus anything. But this theorem says I don't need to use every antiderivative. I just can use any antiderivative. So there's the one I pick. Okay, so I did. But the c I chose was 5. Because over there it doesn't say you have to use, yeah, okay, you're good, I think. Give me a second on that. It's a good idea, I think. But let me go on. Okay, so here the fundamental theorem says take the antiderivative, right? Okay, then what do you do after that? Plug 1 and 0 in and subtract, right? Because it says plug B in, plug A in, and then subtract. So I need some notation that says plug in 1, plug in 0, and subtract. Because we're going to be doing that a lot. So here's some new notation that means plug them both in and subtract. A line and then a 0, 1 means that. Okay, so then I'm going to plug 1 into this. So there I plugged 1 into my antiderivative. Next I'm going to plug 0 into my antiderivative. And then after I figure out both of those numbers, I'm going to subtract. Okay, 1 cubed is obviously 1, so that's going to come out to 1/3. And then 1 to the 3/2 is 1. 1 divided by 3/2 is 2/3. And then for this, that's obviously 0 plus 5, so 5. And then subtract. So now I'm going to take 1/3 plus 2/3, and that's 3/3, which is 1. Then add 5, that gives me 6. Then subtract 5, that gives me 1, right? So what that means is, if I graph this function and find the area under it from 0 to 1, that's going to be 1. The area under this curve, yes. So it's confusing, Bryn, because we've got this other curve. It's not the area under that. It's the area under the original. And you use the antiderivative to calculate the area under the original. Good. Yes, Lane?
Since it can be an antiderivative, can you just treat C as 0?
So, sorry, I should have called on you first. I didn't think he was going to say that. So, yes. So here is what Lane and Rachel have noticed. I could have put a 98 here, right? And if I had, then that would have been 1 plus 98 minus 98, and it still would have been 1. That's why it can be anything. So what Lane is saying is, well, I'm just going to put a 0 here. Or, in other words, I'm going to put nothing there, and that's okay. Now, I will caution you against maybe not putting 0 there. Because sometimes you need to remember plus C, right? So maybe you should at least put a plus 0 there to remember that you're supposed to put plus C in other contexts. Because you're going to forget to put plus C. So if you ignore it here, you might forget more often. So that's why I started out by putting plus 5 there. Yeah.
Does that new notation you showed us acceptable in
Yeah, this is standard mathematical notation. It seems like something I would make up, but I didn't make this one up. This is real. Yes. Okay. So this is powerful stuff, this Fundamental Theorem of Calculus Part 2. It's a really nice, quick way of finding area. Just like the frontwards power rule was a really nice, quick way of finding slope, right? So slope and area, they're more related than we thought. Slope is derivative, area is antiderivative. Okay, let's say we wanted to find the average value. I don't want the word value there, I just want the average of f of x equals the sine of x on the interval 0 pi. Okay, so it's been a while since we did average. We did it before Christmas, but it's been since before that, so it's been last year. Does anyone remember how to find the average? Yeah, Michael.
multiply the interval by 1 over the width of the...
So it's 1 over b minus a times the area from a to b of f of x dx. So at some point, maybe for the exam, you had that memorized. That's the average height of a function. Sometimes we called it average value. It's the average height. If you have a graph, it's on average how tall the graph is. Okay, so for this problem, we want to find the average of that graph. So we're going to take 1 over pi minus 0 times the integral from 0 to pi underneath sine of x dx. Pi minus 0 is obviously pi, right? So it's 1 over pi. Then I'm going to use my new trick to figure out this area. So what's the first step? Take the antiderivative of the sine of x, right? Okay, so the antiderivative of sine of x, sort of cosine, it's negative cosine. The reason that's the antiderivative, we can check by taking the derivative of this and seeing if we get that, right? So the negative 1 is just hanging out when we take the derivative. The derivative of cosine is negative sine, and then negative 1 times negative sine is positive sine. So that's why that is the antiderivative of sine. Because if you take the derivative of it, you get sine. Okay, then we need to plug in 0 and 1 and subtract, right? So, or not 0 and 1, 0 and pi. Excuse me. So you plug in pi. You plug in 0. And then you subtract. This is obviously a non-calculator problem, otherwise we would have been doing math 9, right? So I guess we better do the trig non-calculator as well. So unit circle, pi radians is over here. That terminal point is the point -1, 0. Cosine is the x value. So the cosine of pi is -1. This is the opposite of the cosine of pi. So it's the opposite of -1. So it's 1. Then for 0, 0 radians would put you there at the terminal point 1, 0. Cosine of that is 1. The opposite of that is -1. So we're taking 1 minus -1. 1 minus -1 is saying 1 plus 1, so that's 2. And 1 over pi times 2 is 2 over pi. So final answer is 2 over pi. Pi is kind of close to 3, right? So that's about 2/3. So that means if we graphed the sine of x from 0 to pi, the average height would be around 2/3. Does it look feasible that the average height, that's what that means. Find the average means find the average height. Okay, now we're going back to velocity. Particle travels on a number line again. And its velocity is given by cubed minus 3t squared plus 2t. again, for part A, we are going to find the displacement. On the time interval 0, 2. All right, so it's been a while, but what is displacement? Yes. How far it is from where it started. So we need to figure out where it is after 2 seconds, and we need to figure out where it was after 0 seconds, and then see how far apart those are. So we need to figure out where it was after 2 seconds. We need to figure out where it was after 0 seconds, and then see how far apart those are. That's called displacement. So going back to example 1, I was really doing displacement, wasn't I? I said distance traveled, but the thing was always going in the same direction. So it didn't matter what I called it. Okay, but today we learned that another way of doing this is this. The fundamental theorem of calculus that we learned today says this is method 1, but this is the other possibility, right? Actually, being technical in example 1, this was method 1, this was method 2. They're both displacement, right? Because they're the same thing. So if this was calculator active, I could just math 9 this velocity from 0 to 2. I've done it a few times today. It comes out to 0. What does that mean? It means that it started and ended up in the exact same place. Now, maybe it sat there the whole time, or maybe not. Maybe it wandered off this way and then came back, or maybe it wandered off that way and came back. I don't know. All I know is that its displacement is 0, meaning it started and ended up in the same place. Okay, so now, let's say that it did go this way for a while and then come back. Well, in that event, the velocity graph would be positive for a while, right? Above the x-axis. Because if you're going this way, you have a positive velocity. And then it would be a negative velocity for a while, because you're going back. And then what might be happening is this positive area might be canceling out with that negative area. And that's why we're getting a total area of 0 meters traveled, or a displacement of 0 meters. Okay, so for part B, now I'm going to say, what is the total distance traveled on 0, 2? So that means if I want the total distance traveled, I don't want to count this journey as positive and this journey as negative. I don't want them to cancel each other out. So how can I accomplish that? Yeah, TJ? Just make this negative velocity, flip it up and make it positive, right? And then I'll have 2 positive areas. So if I want the total distance traveled, I need to integrate the absolute value of velocity rather than integrate the just plain velocity. Now back in example 1, I kind of just ignored the fact that I would need absolute values for distance traveled because I knew the velocity was always positive. Remember our velocity graph in example 1? It was always positive, so I knew that that wasn't going to matter. But total distance traveled is technically the area underneath absolute value of velocity, whereas displacement is the area underneath velocity. Okay, so you can math 9 this, and then absolute value is math num, and then 8 maybe, I'm not sure, but something like that. So you could type all that in. And it comes out to half a meter. So this particle didn't wander very far from where it started. It just traveled a quarter meter this way, and then a quarter meter back. And it ended up where it started, so that's why its displacement was 0, but its total distance traveled was half a meter. Everybody doing okay? Okay, now first thing tomorrow, we're going to calculate this without math 9. It's a little bit nasty, but it's possible. So you can look forward to that.